Hello and welcome to section 2, forward sampling. In the previous section, we talked about the fact that exact inferences can be quite computationally costly, and therefore we need approximate inferences. And the one that we're going to focus on in the next sections and this one is particle-based approximate inference. To use this kind of inference, we need to generate data instances based on the model's CPDs, and these data instances are referred to as particles. So some recalls that we need here is how to generate instances given a probability distribution. Well, the idea is that you can draw a random number r between 0 and 1 from a uniform distribution using a random number generator, for example. And then if the probability distribution of interest is a binomial, for example, then you can choose the first value of your x variable, which is binomial x1, x2, if this generated number falls between 0 and its first probability value. Say, for example, a binomial with mean 0.3, then if r is 0.2, it falls between these two numbers, and then you will take its first value, otherwise you will take its second. And in general, you can have it the same idea for multinomial probability distribution. You draw a random number r, and according to which category, which of these intervals it falls into, you will decide on which value your random variable is taking. If it falls between 0 and x1, so these are the probabilities. So imagine you have with probability px1, it will take value x1. With probability px2, it will take value x2, and so on. Then if the value of r falls between 0 and px1, like here, then you will take x1. This length is px2, and the whole thing here is px1 plus x2. If r falls between px1 and px1 plus px2, then you will take the second one, and so on. Same story with conditional probability distributions, just that this time we have everything conditioned on x2 to xn. For example, if we are interested in sampling x1 from this CPD, okay, like here if we want to sample, say, C from this conditional probability distribution P of C conditioned on M, it's exactly the same story, just that now we will have P of x1 conditioned on the values of x2 to xn. Okay, at the end of the day, this will be just some number between 0 and 1. Okay, so now that we know how to generate instances from probability distributions, let's see the idea of forward sampling in practice. We are given this network and we are interested in the probability that the person does not wear a mask and has COVID. We answered these type of questions in the exact inference section. Now we want to do it using approximate inference. Well, we need to sample particles given the CPDs, and this means that we need to generate random numbers to assign values to m given P of m. So for example, we can get m0 here, and we need to generate random numbers to assign a value d given pd. So for example, here we may get d1. And if we have these two, then we can generate a random assignment for COVID given m and d that we already generated. So it will be, for example, c1 given that we have m0 and d1. And this will be our first particle or data instance. Okay, so the idea again is to first generate these instances, and then we can calculate the probabilistic query. So let's see how we can do this. So we need to generate a set of particles d as we just explained, and this is basically p of y that we're interested in. So how can we do it? Well, it's basically that we first sample mask, and for mask we saw that it had two values, 1/3, 2/3. So we generate a random number R, and then based on which interval it falls into, then we decide between these two values. So in this case, for example, imagine we sample M0. Next, we go with social distancing. And again, this one has either D0, D1, which it had same probabilities. So we go, imagine this time we get D1. And then we decide on the value of COVID. In this case, COVID for M0, D1, the only possibility was C1. So we will get exactly the value of 1. If we were here, then we had two possibilities, and the value of COVID would be sampled based on these two values again. Now, the ordering here, we could have social distancing on the top and then mask beneath it, but then COVID, in order to sample COVID, we really need to know its parents. Okay, so this will give us our first particle, or first instance, M0, D1, C1. And then we will repeat the same procedure to get more particles. Okay, 2, 3, 4. Once we have all of these, then by definition, so we can calculate the query of interest. So this will be the practical distribution, M0, C1, and it's just the number of particles with M0 and C1, which is just 1, divided by the total number of particles. So here it will be 1 over 4. Okay? So forward sampling is kind of the simplest approach to generate particles, and here's the algorithm. We go with some topological ordering of variables in X in a Bayesian network. For each of these, we go one by one. If xi has parents, then we sample it from this distribution, p of xi, condition on the values of its parents. Otherwise, we will just sample p of xi, okay, from p of xi. And then we will assign sample values xi to xi, and we will put it back in this distribution. Okay, so the probability of event y, given the set of particles here d, 1 to capital M, then can be calculated in this way. So I'm putting hat because it's approximating the probability of interest, and we have d here because it's based on this data set. This will be the average of 1 over m, so the average of the number of times that our particles matched the event of interest. Okay, so we just count. This is basically counting the total number of times we had the event of interest appearing in the data set divided by the total number of instances. And this notation means that ym, it's like extracting the values of the set of variables y from instance m. Same set of particles d can be used to estimate the probabilities of multiple events y, and this is one of the benefits of this approximate sampling or inference. Okay, we don't need, if I want to calculate another event, I don't need to redo the whole process. Once I have the data set, I can do all of that. Okay, let's see it in practice again. We talked about the probability of M0C1, and using 4 particles, we saw that the probability will be 1 over 4. Now, analytically, back to the exact inference, and using the joint distribution, we can see that this probability is quite different. It's 1 over 2. Okay, so just by p of m0, p of c1, condition on m0 and d, and marginalizing over d, we will get this value. Then this brings us to the question of how many particles actually are required to obtain a good estimate. And it appears that we can answer the question by looking at the dataset D as a sequence of m independent Bernoulli trials, where The success is when the event the event of interest y appears in the instance or in the particle. So just recall that a Bernoulli trial has only two outcomes, success and failure. The success is with probability t, otherwise 1 minus p. So it's basically the same as like if you have an unfair coin and say tails happens with probability 0.6, and you just flip it for say m times. You want to know how many times you need to flip it so that the number of tails that appears compared to the total number, this ratio represents 0.6. Okay, so here the success is py. This is what we're interested in, and we want to know how many times we need to sample the particles m to get close enough to py. And for this we can use either the Hoeffding or Chernoff bounds. Recall to these two bounds, consider D as a sequence of m independent Bernoulli trials Tm with success probability p. The estimate of p based on D, it's defined in this way: the number of times that success happens divided by the total number of times. Now, the Hoeffding bound says that, this is also known as the absolute error bound, it says that the probability that this estimate is away from the actual value, the p, by a distance of more than epsilon, it's bounded away by this value. So the probability that this estimate is too far from the actual value, and by too far I mean more than epsilon, is this small. Okay? So suppose that we say we want to bound this to small value that I just said by delta, then we get that m needs to be at least this value. Okay, this is how the Hoeffding bound helps us. Similarly, for the Chernoff bound, the relative error bound, we have that the probability that this time the estimate falls epsilon% above or below the actual quantity of interest, the probability p, it's bounded by this value. Okay, so if I want this value, if I want the probability that this not desirable situation happens to be bounded by sigma, then I have the minimum required number of samples bounded from below by this number. Now, the point is that here we see in the denominator the value p appears that I don't have access to. It's actually the one that I want to estimate, and this can make things complicated. I will soon talk about this. Let's just turn all that we just recalled into the forward sampling framework. So again, we want to estimate p of y. Then the Hoeffding bound translate into this form. The probability that the estimate of the probability of y, or let's just say the estimate, exceeds by value epsilon of the true value, the true probability, is bounded by this value. And therefore, if I want this whole probability of making an error to be less than sigma, then the required number of samples is this value. I get to choose delta, I get to choose epsilon, so I can easily calculate this. Okay, now the Chernoff bound though, then I will get this value at the end, and you see that p of y is appearing in the denominator, okay, which I don't have access to, and it's unknown. Okay, back to our forward sampling question. The answer using 4 particles, we saw that it was 1/4. How many particles are required to obtain a good estimate? We saw that the actual value of this probability is 1/2. So if we want to have a probability of exceeding the true value, which is 1/2, by the value 0.03. So meaning that I want to get at most 0.53 or 0.47. Okay, the probability that this does not happen, so that my estimate falls out of this interval, if I want to have that probability as low as 5%, then I need 2050 particles. Okay, so if you do this, still there's 5% probability that you fall out of this interval. Okay, but it just depends on how confident you want your estimate to be, and based on that you can choose these two values. Now instead, if you say that I want to have my estimate to at most 3% off of the true value, and the probability that this being off or making an error to be 5%, then we should use the Chernoff bound, and then we get the minimum number of required particles as 2050 times 6 over this value, p of y, the true value, which is clearly between 0 and 1, and therefore this number will be more than 2050. You may say, well, why to go through all this trouble, and why don't we just always use this? Well, imagine that the py that we're interested in is already a very small number. So say it's 0.001. Then bounding it to be for your estimate to be like 0.03 away from it, that may not make much sense. If you're dealing with already very small numbers, and if you don't know that number, if it's how small it is, then using this approach, at least for large values of epsilon, will not give you the desired estimate. Okay. Okay, so to summarize, how does forward sampling generate particles in a network? For example, in this one, we can generate the particles in parallel. That's the important point. But we need a topological order, meaning that we cannot first sample COVID. We need to first sample mask and then social distancing, or the other way around, and then sample COVID. So here you see that we call it time or step T, and that is like the steps that we go through when we're sampling these values. So first, that is like time t equal to 1 or step t equal to 1, we're doing mask, and then time t equal to 2, social distancing. We use the values of both of them, that's why we have these arrows, to do the last one. We will use this notion of time or step t later on. That time may not be the best notion here, but it's good because it's indicating like how in practice we would implement it. It's first this should happen, then this, and then the last one, this one. Okay. So forward sampling, what about conditional probability queries? Well, there are two approaches to obtain particles from the posterior probability distribution, p of y condition on z. So far we were only focusing on p of y. But now what if we have some evidence z? Well, one way is to do rejection sampling, that is to generate particles from p of x as before and reject particles not compatible with z. Okay, so for example, we do this, and we may see that, for example, this one does not match our particle. So for example, we want the value of d to be set to d1, then we would reject this row, and our data set will contain only these 3 green ones. Once we do that, we are basically conditioning already the distribution on z. Then we will compute the ratio of particles satisfying event y to the total not rejected particles as before. Then the expected number of non-rejected particles is m times p of z, and because the number of variables in the joint distribution can be many, the probability assigned to each event can be very low, right? So p of z can be basically extremely small, and we need m to be quite large to get MP of z non-zero to make it a meaningful probability. Okay, so it requires quite a large number of sampling. The other way is to use separate estimators for P of z and P of y and z. I mean, either way, we require a high number of particles m. We saw that for given the bounds, for example, we saw that this can be quite large. So what can we do in this particular case of conditioning? How can we calculate this probability? And this is the subject of the next sections. Thank you.